Hi guys. All right, so we are about to dive into our very first proof, which is a really big deal in geometry. That's why I'm hopping on and doing a quick video instead of just typing things up for you. So before we get into the proof, there's a couple things I need to make you aware of. First, we're going to be proving the vertical angle congruence theorem. Before I start the proof, you need to know what vertical angles are. Now, you should know this from middle school, but just in case you don't, I'm going to real quickly go through the definition. The definition says two angles that share a common vertex and their sides to form pairs of opposite rays. Now, that sounds kind of complicated, but let me just show you real quick what it's talking about. So, two angles that share a common vertex. So, here's a common vertex between all four of these. But that second part where it says they have two pairs of opposite rays, well, this ray would be considered opposite of this, and this ray would be considered opposite of this. So that means that angle 1 and angle 3 would be considered vertical angles. Also, angle 2 and angle 4 would be considered vertical angles. Okay, so that's what a vertical angle is. Now, the vertical angle congruence theorem is exactly what it sounds like. It says that if two angles are vertical, meaning they fit that criteria, then they are congruent. So, what we are going to do now is we are going to try and prove that theorem. Anytime you have a theorem, the goal is to be able to prove it. Now, there are theorems out there that mathematicians use that have never been proven. The Riemann hypothesis is a theorem that's never been proven. The Goldbach's theorem has never been proven. These are theorems that we pretty much know that they're true. We use them in other math, but people haven't figured out how to prove it yet. Meanwhile, other theorems are proven so much it's ridiculous. The Pythagorean theorem, probably the one you're most familiar with, has been proven over 300 unique ways. It's been proven tons of, not a million, 300. It's been proven a ton of times. But for this class, we are going to attempt to prove every theorem we come across before we allow ourselves to use it in future problems. Okay, so we are going to prove the vertical angle congruence theorem. Now, why haven't we proven anything so far, you ask? Well, there's a very good reason, because so far we haven't really used any theorems. Instead, we have looked at postulates and definitions. So when we looked at here, we have supplementary angles. The definition of the supplementary angle is that it adds up to 180. We don't have to prove that. It's a definition. It's what supplementary angles are. The linear pair postulate, I think was... Oh, no, I went too far. The linear pair postulate is a postulate. Postulates are basically the same as theorems, but we don't have to prove them. Okay, so it says right here, we don't have to prove definitions. We don't have to prove postulates. Okay, so far we've been able to just use things without proving them. But now we're going to get to our vertical angle congruence theorem. All right, so back over here. Now, the kind of proof that we are going to focus on mostly in this class is what's called a two-column proof. It's a bit of a misnomer because actually we've got 3 columns, but the first column is just numbering your steps, just helping you keep track of how many steps you've got. The two main columns are our statements, or the claims that we are making, and our justifications. So your statement is going to be, here's the fact that I think I know, and then your justification is, here's the math, the theorem, the postulate, the definition, the property. Here's why I'm able to make the claim I just made. All right, now, starting a proof. First thing you got to do when you're starting a proof is think about the end. Think about what you're trying to get to. So for example, this says that the vertical angle congruence theorem is if you have two vertical angles, then they are congruent. So if I'm going to prove that to be true, I need to prove that no matter what vertical angles I'm given, regardless of if the two lines are crossing, I can't get it. Okay. If the two lines are crossing like this, where it's making two really obtuse angles and then two really acute angles, or if it's more like at a 90-degree angle, it doesn't matter. No matter where the two lines cross, they're creating congruent pairs of vertical angles. That's what we need to prove. So we need it to be as generic as possible. If we need it to be congruent, we have to think, well, what does it mean to be congruent? the definition of congruence is that the two angles will be equal in measure. Okay, so that tells me my last step needs to say, here are two vertical angles. The step right before that, the penultimate step, needs to say these two measures are equal, because that's what's going to allow me to show that they're congruent. Now, I could choose angle 1 and 3 to prove to be congruent, or 2 and 4. It doesn't matter, because they're both just generic angles. I don't know what the measure is. This is asking us to prove 1 and 3, so that's what we're going to focus on. All right, so the beginning of every proof, not every proof, but most of the time, the first thing you're going to do is see what information is given to me, because you've always got to have a starting point. In this case, we have given you that angle 1 and angle 2 are a linear pair, and angle 2 and angle 3 are a linear pair. So these two are linear, and these two are a linear pair. Now, we didn't actually have to be given that, because we can get that information from the diagram. So if this had not been there, you would have just said, you still would have started out by saying angle 1 and 2 are a linear pair, but your justification would have said given in the diagram. As it stands, though, since we have those two statements, then we can just start it out like this. Step 1 is that angle 1 and angle 2 are a linear pair. Angle 2 and angle 3 are a linear pair. And the justification for that claim is that it was given. That's given information. It's free. We like it when there are givens, 1, because it's free information, and 2, because it kind of gets our brains sort of going down a path. It gives us a starting point. The reason, normally we try to keep just one statement per step. In this case, we've got 2 separate statements, and that's because they have the exact same justification. Sometimes you'll want to still keep those separate. It kind of just depends on the complexity of the proof. Okay, so where do we go from here? Well, what you're going to do from here is you think, okay, I know that they're linear pairs. That has to give me more information. So what's the next logical step? Well, if I know they're linear pairs, well, we learned the definition of a linear pair is that the two angles are supplementary. So if you go back and look at your notes at the definition of a linear pair, it says that that gives you supplementary angles. So that means that for step 2, I can say angle 1 and angle 2 are supplementary. I abbreviated that. It doesn't matter. And then angle 2 and angle 3 are supplementary. Again, I can have those 2 statements in the same step because they have the exact same justification, which is the linear pair postulate. If we go back and look at that linear pair postulate, it says if 2 angles are a linear pair, then they are supplementary. So that's why we're able to say this. Okay, now I'm still not seeing anything equal or congruent or anything like that. So I'm just going to keep trusting the process, and I'm going to keep trying to go through and think, okay, I knew they were a linear pair because it was given. I knew they were supplementary because linear pair postulate says so. What does it mean to be supplementary? Well, the definition of supplementary, I just showed you and reminded you just a moment ago that the definition of supplementary is that they add up to 180. And this gets me excited because a lot of the time, not always, but often, especially at this level of math, a proof that is going to be easily proven is one where we're able to take words and geometric ideas and translate it into an equation. Because as soon as you've got an equation, now we're cooking with gas. Now we're using those algebra skills that we've been working on for years to solve the rest of the problem. So I can take this statement right here, and in my brain, it's already translating into an equation. And that equation is, well, that means that the measure of angle 1 plus the measure of angle 2, I flew up to the top. The measure of angle 1 plus the measure of angle 2 is equal to 180. And then the same way, this sentence here gets translated to measure of angle 2 plus measure of angle 3 equals 180. And now I'm excited because once I've got an equation, I can start using algebra properties that I'm more comfortable with. And the justification for this is the definition of supplementary angles. What it means to be supplementary is that the measure of the 2 angles adds up to 180. Okay, so now, where are we going to go for here? We've at least got an equal sign, which is a good step because we know we're trying to get to the point where we can say that the measure of angle 1 is equal to the measure of angle 3. But I've got two equations. In algebra, you should have learned about, and in your previous math class too, you should have learned about systems of equations. When you've got two equations and multiple variables, one of the methods we use for solving it is by substitution. Here, I know that the measure of angle 1 plus the measure of angle 2 is equal to 180, and also the measure of angle 2 plus the measure of angle 3 is equal to 180. Well, if I've got two things that are both equal to 180, then that must mean these two things are equal to each other. So I'm basically just using substitution. I'm going to say measure of angle 2 plus measure of angle 3, and I'm going to substitute it in for that 180 because it's equal to 180. Okay? And the reason I'm allowed to do that is the substitution property of equality. Okay, you may not have known that that was the name of that property, but that is something that we used all the time in algebra, especially when we were doing those systems of equations. Now, I'm excited because now I've got an equal sign, which I knew I needed, and I've got angle 1 and angle 3 in the same equation. I just got to get rid of those pesky 2's. Well, luckily, I've got measure of angle 2 on both sides. This is just solving an equation. I am going to imagine myself subtracting off. You don't have to always show this step, but I'm allowed to subtract this measure of angle 2 as long as I subtract it from both sides of my equation. And that's called the substitution property of equality. I did a drum roll and then said the wrong thing. It's the subtraction property of equality, which says that I can subtract the measure of angle 2 from both sides, and it leaves me with measure of angle 1 equals measure of angle 3. And I'm almost done, except remember, we're trying to prove the vertical angle congruence theorem, which says that they are congruent, not equal. And while we know that those are very similar ideas, they're not identical. So my last step is going to say, well, if I know that the measures are equal, then I know that they're congruent because the definition of congruent angles says if two measures are the same, then they are congruent. And I had a copy and paste fail here. This should not have an M anymore because once you're into congruence, you're not talking about the measure, you're talking about the angle as a whole. So this should say, here, I'll just rewrite it all together. This should say angle 1 is congruent to angle 3. And now I'm done. And the way we finish proofs is you either put a little box that just means done, or you put QED, which is Latin for quid est something. I always forget what the last letter stands for. I don't know. Basically, it means thus it's determined. It has been decided. This is proven. And you're done. All right. So hopefully that made sense. We're going to go through a lot of these as it goes. As we go through the course, some of them you will get to do on your own, but we're going to give you lots more practice before we get there. So let us know if you have any questions, and good luck. Have a math-terrific day.